Okay, in this video lesson, we're going to focus on what's called free fall motion. This is an application of one-dimensional motion. Instead of looking at things moving left or right or forward, backwards, instead now we're looking at things going up and down, and specifically when things are falling through the air. So free fall motion is the motion of any sort of object when it's under the effects of gravity only. So some examples would be falling objects. So say I'm standing on top of a cliff and I drop an object towards the ground. That object is going to fall, and it's going to fall due to gravity. Gravity is the thing that's pulling it down towards the center of the earth. Same thing is true if I were to throw an object up in the air. So if I throw it straight up or possibly throw it at an angle so it goes a little bit forward, again, it's going to go up to some maximum height and fall back down, and it does that because of gravity. Without gravity, an object that's dropped would just float there, and without gravity, an object that's thrown would continue to move straight up in the air, or if I threw it at an angle, would continue to move up in the air at an angle. So gravity is the thing that pulls things down towards the earth. Now, how does this relate to what we've been talking about? Obviously, we spent a lot of time looking at the variables of motion and how to represent them. So you'll see here that as I track free fall motion, let's say as a dot diagram, you'll see that as the object falls towards the ground, you'll see the spacing between those points get larger and larger, which is showing that as an object falls towards the ground, it's speeding up. Same thing can be seen when I throw an object up into the air. As it's going up into the air, you'll see the spacing between the dots starts large and gets smaller, showing that as I throw something in the air, it's going to slow down until eventually it reaches that maximum height. And then it'll start to fall back down. You'll notice the same thing in reverse. As it falls down, it starts to spread out a little bit more, meaning it's speeding up. And same thing would be true if we're throwing at an angle. The only difference between throwing at an angle, which we're not going to look at in this section, is that the object is moving forward as it moves up and down. We're actually going to look at that in a separate unit. So today we're focusing on free fall motion. We're going to analyze the effects of gravity on objects. All right, as we just talked about, as an object is falling under the effects of gravity, we see that the spacing between the dots gets larger, or in reverse would get smaller, which means the object is accelerating. Now, an acceleration, again, is when objects gain or lose speed. So for an object that is falling towards the ground, what is causing it to gain speed? Well, in order to accelerate, something has to be causing you to do that. It has to be caused by either something pushing on you or pulling on you or resisting, whatever it might be. So if we think of an object falling towards the ground, the thing that causes it to fall is gravity. So when an object is falling towards the ground and is accelerating, it is accelerating due to gravity. Gravity is the thing that's pulling this down. So to show us, if I were to track its velocity vectors, as it goes down, the blue arrows as it falls down would get longer and longer. That means it's accelerating. And because it's speeding up, that means it's going to face an acceleration that's also pointing downward. And like we talked about, it's going to face a constant acceleration that's always going to be the same, meaning it's going to gain the same amount of speed every second, meaning it's going to get faster and faster and faster. And what was found out is that it actually is going to gain a set amount of speed. That gravity is always going to cause objects to speed up or slow down at the same rate, no matter what type of object they are. And that rate is 10 meters per second every second. Okay, so 10 meters per second per second. You will see that sometimes labeled as G, and G is just our symbol for gravity, which we're always going to fit this value of 10. Now, for those of you that might have seen this in a different class, you might recognize that gravity is not exactly 10. It's actually around 9.81 meters per second every second. But in terms of this class, we're going to just round that up to 10 because that's a nice, easy number to use. So what that means is that if I take this object, say I drop it from rest, it starts at 0, every second it's going to gain 10. So it's going to go here from 0 to 10 to 20 to 30 to 40 to 50 if I were to draw that blue arrow there. And again, that green arrow, which represents the acceleration, notice it's plus 10, plus 10, plus 10, plus 10, and so on every single time. So it's going to gain 10 meters per second of speed as it falls. So putting this all together, as it falls, we have kind of a little relationship here. This is a formula that I'm going to give you guys. To find the speed of an object and kind of relate that to the time at which it's falling or thrown up in the air, we can use this simple formula. So V equals G times T. So as you see here, we have three letters. V is going to stand for the speed of the object. G is going to stand for gravity, which is going to be that value of 10. And then T stands for time. So how this equation is going to be used is, let's say I drop an object towards the ground. I want to know how fast is it going 3 seconds later. Well, 3 times 10, if I know G is 10 and T is 3, 3 times 10 would give me 30 meters per second. Now, to flip that in reverse, it would be the same thing if I were to throw an object into the air. I can also analyze that relationship using this equation. Same thing can be done, and this is more so for objects thrown up into the air, but I can also relate that to the height, okay? The idea is this, is that if I take an object and drop it, the higher up you are, if this cliff was longer, the more time it's in the air. So there's a relationship between the height and the time. Similarly, if I throw this thing up into the air, the more speed I give it, the higher it's going to go, and the higher it goes, that means the more time it's in the air. So the second relationship we have is to figure out the distance, which I have here labeled as h, so height, in relation to an object that's either thrown or dropped. So h here is going to stand for height. G again is that gravity value, which is always going to be 10. And then T again stands for time. All right, so we can use these formulas to try and analyze problems of things going in free fall. So we're starting to get a little bit mathy here instead of just looking at the diagrams of free fall motion. So this idea of free fall motion was first analyzed a long time ago by Galileo, and it was Galileo's one of his original thought experiments that led to the ideas that Isaac Newton came up with, and you guys might know from like the apple falling from the tree and so on and so on. The idea is that if we think of an accelerated motion, so something gaining speed, that if I place, let's say, a ball on a flat surface, that ball shouldn't move. But as soon as I give that surface some angle to it, that ball is going to speed up. And then if I increase the angle of that surface, the ball is going to increase its speed, and it's going to speed up at a faster rate than it did before. And to maximize the rate at which it falls is if I were to place the surface vertically so that the ball doesn't even go down the surface, it just falls to the ground. And in this situation, when it just falls to the ground, is when it's going to experience the greatest acceleration. It's going to pick up its maximum speed, and it's eventually going to travel at its fastest. And that's where the concept of free fall motion comes from, okay? Now, part of Galileo's little thought experiment is this. What if then I were to drop different objects? If all objects are going to move their fastest when they're falling to the ground, are there other things that are going to affect how fast it falls? So a common thing would be, and this is something he tested, he didn't really test the hammer and the feather, but let's say that I had a hammer that I was going to drop to the ground, and at the same time, let's say that I had a feather that I was going to drop to the ground. If I were to drop a hammer versus a feather and let them fall to the ground, and let's say the ground was here, which one would hit the ground first? And one common misconception, it's something that we see in everyday life, is how objects fall. That obviously if I drop a hammer and a feather, the hammer should hit the ground first. But what Galileo said is that all objects are undergoing this free fall motion because gravity is the thing pulling them down. And gravity doesn't matter if it's a feather or a hammer. Gravity is going to act on all objects the same. And that then led to Newton figuring out, okay, that's true. Gravity is going to affect all objects at that rate. So why then does a feather hit the ground first? So to show you this relationship, this was actually something that we didn't really test to be true until we landed on the moon. So this is an actual video from the Apollo 12 mission when they were doing some experiments on the moon, and one of them they did was to drop a hammer and feather at the same time from the moon to see which one would hit the ground first. Now, what's the difference between the Earth and the moon? Is that the moon doesn't have an atmosphere. It still has its own gravity because the moon is made of stuff, but it does not have an atmosphere which affects this. So take a watch here.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that is for show, folks, right? Hammer and feather hit the ground at the same time, proving Galileo to be right that all objects undergoing gravity are going to fall at the same rate no matter what they are. All right, another video to show you. This is the same thing, but this is on Earth. The guy's going to drop a bowling ball and feathers. So very similar to a hammer and feather, you have a heavy object and a light object. So let's take a look at what happens here. Now understand that obviously the bowling ball hit the ground first, and the reason why is because the bowling ball is heavy, right? And that's incorrect. It's not that the bowling ball is heavy, it's that because of its shape and its, I guess, density, it flies through the air better than a feather does. The feather undergoes what's called air resistance, and it doesn't fall at its maximum rate. So I'm going to show you a second part of this video where they're then going to take the air out of this chamber, because this is technically what's called a vacuum chamber. So they're going to suck all the air out, eliminating any atmosphere inside that chamber, and they're going to drop the bowling ball and the feather once again. Let's take a look. And here we go.
Release.
Now remember, there's no air in this chamber. It's a little slow-mo. The thing that blows my mind as you watch this, folks, is look at the feathers. They don't even move. They stay in their shape the entire time.
Look at that.
Folks, that's just craziness right there. That is just craziness. That's physics right there, babes. So what this is showing is Galileo was correct that all things are going to fall at that same rate of 10 meters per second every second. How neat is that, babe? So we're going to get into our examples now. So what we're going to make the connection between is this idea of falling objects and the idea of gravity. And gravity, again, is what pulls all objects, and all objects are going to undergo that pull, causing them to speed up or slow down at a constant rate of 10 meters per second every second. So what we're going to focus on here is what that number does. And first, that number, strictly acceleration affects speed. So as an object falls, it's going to speed up. So what that number again tells us is that as an object falls, it is going to gain 10 meters per second of speed every second. So if it starts here at 0, 1 second later, it's going to go at 10 meters per second. Another second later, it goes to 20. Another second later, it goes to 30, 40, and 50. So as an object falls, it is always going to undergo that same pattern of gaining 10 meters per second every second. Now in terms of distance, we look at the spacing between the objects, okay? Now I want to show you guys the idea of what goes on with the spacings, but to do this, we're going to use that formula that I gave you guys in the previous slide, or a couple slides ago, where that distance is related to not only gravity, but time. So if I want to find the distance it falls in 1 second, I can't just add 10 like I did before. It's not that simple. But instead I use the formula 1/2 of 10 times the time, which is 1 squared. So math-wise, half of 10 is 5. 1 squared is 1 times 1. That's 1. So 5 times 1 would give me 5. That's a little mental math there. If I did again, half of 10 times 2 squared, well, half of 10 is 5 again. 2 squared, 2 times 2 is 4. 5 times 4 gives you 20. And then I would do half of 10 times 3 squared. So half of 10 is 5. 3 squared is 9. 5 times 9 is 45. And then I'll do half of 10 times 4 squared, one of my favorite games, that's going to give you 80. And then if I go 1/2 of 10 times 5 squared, that's going to give me 125. Okay, so those are the distance values. Now I just want you to watch this real quick, okay? So if I look at the changes, right? So it goes from 0 to 5, that's plus 5. It goes from 5 to 20, which is plus 15. 20 to 45, so plus 25. 45 to 80 is plus 35. 80 to 125 is plus 45. So notice there is technically a pattern. It is going up, and not going up by the same amount every time, right? But I do want you to see this then. What's the difference between 5 and 15? Well, that's plus 10. 15 and 25 is plus 10. 25 and 30 is plus 10. 35 and 45 plus 10. So notice there's that constant of 10. It's going up by the same amount of speed, that value of 10 every single time. And that value of 10 is gravity. So it's always gaining 10 meters per second of speed every second. Now, next example, there is a second part, part B. I want you guys to cancel that one. We're just going to look at A here. So what happens if I throw a ball straight up in the air? So let's say now, instead of dropping it, that I throw it. And let's say I throw it up in the air to start at a speed of 40 meters per second. To show you with our diagram, I'm going to draw arrows to represent speed. So it goes up, and then notice as I draw these arrows, how the arrows get smaller, and then it's going to come back down and the arrows get bigger. So here's what happens again. Anytime something is thrown or dropped, it's always going to change its speed by that ratio of 10 meters per second each second, or by that rate, I'm sorry. So what that means is as an object goes upward, it's not gaining speed, but it's losing speed. But this value still holds true. That if it starts at 40 meters per second, 1 second later it's not going to gain speed, but it's going to lose 10. So it's going to go 30 meters per second. Then instead of gaining 10 again, it's going to lose 10 to go to 20, then to 10, and at the very top it'll go to 0. So at the very top of its motion, it's not technically moving at all, but then it naturally starts to fall back down. It doesn't just float there, floats for an instant, then it falls back down, and it's going to fall back down, gaining that same 10 meters per second every second. So it would go 10, then to 20, then to 30, then to 40. So a key thing here to realize is that notice how both the up and the down kind of look the same. The only difference is the direction in which it's going. Okay, so that gravity is going to be constant no matter if it's thrown or if it's dropped. All right, last two examples here. We're just going to get into some problem-solving things. So now here, using those two formulas, in A, we have a bird that drops a turd. Hey, that rhymes. A height of 750 meters, and I want to know how much time does it take to hit the ground. So again, all objects are going to fall at that rate of 10 meters per second each second. So the two things we know is that we know the relationship of gravity and time that affects the speed. So every second it's going to gain 10 meters per second. We also have the height formula that relates, depending on its height, how much time it would take to hit the ground. Okay? So in this case, if the ball is dropped from a height of 750 meters, I know my height is 750 meters. So if I want to find the time it takes to hit the ground, I'm going to use my height formula. My height equals 1/2 gt squared. So if I just plug things in, I know the height is 750, g is always 10, and then t is what I'm solving for. Now this is a little tricky because we're getting some math here, but it's nothing too crazy difficult. 750 is by itself. Half of 10 would give me 5, and then t squared. Now understand these two things are multiplied, so if I want to solve for t, if I divide both things by 5, that's going to give me t squared left on this side. Then on the right side, that's going to simplify down to 150, 750 divided by 5. Now the last part here to solve for t, notice it's t squared. So if you learn this in math, to solve for t anytime something's squared, we want to square root that other value. Okay, so by square rooting 150, that's going to tell us what our answer is going to be. And we're going to put this in a decimal form, but I should get a time of about 12.2 seconds. Not an exact time, but we're going to round that to a decimal. So using that formula to relate the height and the time for something that's falling. All right, in B, we have loosen up. Loosen up. Oh, throws a football straight up in the air. He's trying to loosen up. I get it. Throws a football straight up in the air at a speed of 25 meters per second. And I want to know what's the maximum height to reach. So in this case, we're going to use that height equation again. 1 half gt squared. So I'm going to find the height. That's the thing I'm trying to solve for. In order to find height, I need to know what time is. So we got 1 half of 10 times t squared. Now what the heck is time? Notice here they give me in the problem a speed of 25 meters per second. So speed is not time. But here's what we know. If an object is thrown up in the air at 25 meters per second, that as it goes up in the air, it's going to slow down, eventually reaching 0 meters per second. Now I just got to figure out how much time would it take to reach that. Well, here's what happens. If it starts at 25, we know that it's going to lose 10 meters per second of speed every second. So it'd go from 25 to 15 to 5 and then down to 0. Okay, so 25 to 15 would be 1 second, then 2 seconds, and now think, if it's losing 10 every second, how much time would it take to lose half of 10, which is 5? That should be a half a second. So this is total time going to be 2.5 seconds that it's in the air. Now what's a quick way to do it? If I started off with 25, and it's a time of 2.5. If I just take 25 and divide it by 10, that gives me a time of 2.5. So I'm going to plug 2.5 in there, and then all I got to do is use my calculator to figure out what that is. Kind of going back to the earlier problem. Half of 10 is 5. 2.5 squared would give me 6.25, and then total would be about 31.25 meters for its maximum height. All right, so these are some challenging problems because we are doing a little bit of math here, but now again, free fall motion is just an application of the things we've been learning, throwing a little bit of interesting stuff here with gravity. If you guys got any questions, jot those things down. Otherwise, we'll see you next time.